Question 16. Sir Humphrey Davy discovered several elements including sodium, potassium, magnesium, calcium, and strontium. Explain which block in the periodic table sodium and magnesium belong to. You can see that sodium and magnesium, this is sodium and magnesium, belong to the S block. So this is the S block. That meant that the last electron in the outer shell of sodium and magnesium, the last electron in the outer shell is in the S block. So that's why they're in the S block. So that outer shell electron is 3s, because this one is the 1s, and that's 2s, and that's 3s. Question B. A sample of magnesium, the relative atomic mass is 24.305, is found to consist of 3 isotopes. The accurate relative atomic masses and percentage abundances of 2 of the isotopes are shown in the table below. Determine the relative atomic mass of the third isotope of magnesium in the sample. Give your answer to 5 significant figures. The relative atomic mass is sum of the abundance times mass. So we got the relative atomic mass, that one, and with times in them, that equals to, using the formula, this first one here times that. So you get that times the abundance here times the mass, abundance times that, plus, that sum means plus, so plus that one times that, so 10 times that one, which is that one, right? The third one here is missing, so that's x. The third one is missing x. This one should add up to 100, and the difference is 11.01. So that's the difference between that from 100. Add this together and take away from 100. You're going to get 11.01, because they all have to add up to 100. So this is x, and that's 11.01. So you do x times 11.01, and you divide everything by 100, because it's in percentage of 100. So that will be what the relative atomic mass will be. Right, so I times that by 100, that times that gives me that, and that times that, plus that times that give me that. When you add them all up, that becomes 11.01x, because x times that is 11.01x. Remember, this is x, the third one we're looking for is x, and this is 11.01. All I did was add that together and take it away from 100, I get that. So now I took this one to the other side, or I take away 2144.4351 from both sides, and then I get that goes there, and I get that value, and I divide it by 11.01 to get x. So basically I'm finding x. So I move that to the other side, that becomes minus, and I get that difference. And I divide both sides by 11.01, I get that. And x divided by that, I get this. It has to be in 5 significant figure. 1, 2, 3, 4, 5. So the question says in 5 significant figure here. So that has to be in 5 significant figures. C, a student adds an excess of calcium hydroxide to water in a test tube. In a separate test tube, the student added an excess of strontium oxide to water. 1. Write the equation for the reaction of calcium hydroxide with water. State symbols are not required. C. A student added an excess of calcium oxide to water in a test tube. In a separate test tube, the student adds an excess of strontium oxide to water. 1. Write an equation for the reaction of calcium oxide with water. State symbols are not required. Okay, so that's calcium oxide plus water will give you calcium hydroxide. Make sure that the conservation of mass is applied. 1 calcium 1 calcium, 2 oxygen, 2 oxygen, 2 hydrogen, 2 hydrogen. So the conservation of mass is observed or conserved. Part 2 suggests the approximate pH of the two solutions formed in the test tubes. The pH of calcium oxide and the pH of strontium oxide. Well, calcium oxide will be sparingly soluble. That means it will be slightly soluble, while the strontium oxide will be more soluble. So if this is slightly soluble, that means the pH will be less. And if this is more soluble, that means the pH will be more. Remember, they are both of them are base. So I'm expecting roughly pH 12 and pH 14. Okay, this is, as I said, sparingly soluble. That means slightly soluble. And so therefore the pH is about 12. And this one, the more soluble one, the pH is about 14. Just to see that the strontium will be similar structure. It's a base as well. It's OH minus. So you got OH minus there, the base, and OH minus here, which we call alkaline. And that's why it's a base as well. So question D now. The table below shows enthalpy changes involving potassium, oxygen, and potassium oxide. So that's K2O. And so we've been given these enthalpy changes here. 1. The incomplete Born-Haber cycle below can be used to determine the lattice enthalpy of potassium oxide. In the boxes, please complete the species present in the cycle. Include state symbol for the species. So the first one here, you've got the K, the state matter, state matter. So that means in the existing state. So but that's potassium is solid, and that's where you got potassium there. And you got oxygen as a gas, but you only need a half oxygen. You don't need a whole oxygen. So oxygen is 2 of them. If you divide it by 2, you get 1. That's why you got 1 here. So now what you've done is you've atomized the oxygen from oxygen gas to just 1 oxygen atom, because you've divided 2 here by a half, you get 1. So we call that atom enthalpy of atomization. So that's what that is, of oxygen gas. And then once you've atomized that, the next thing here is this is solid potassium, so you atomize that into gaseous state. So that's enthalpy of atomization for potassium. So you're going from solid to gas. So now you got potassium as a gas plus oxygen as a gas. Then you want to ionize that one. So that's enthalpy of ionization. So that goes from there to become potassium. But you don't need 2 of them because you need 2 potassium. Alright? So you need 2 potassium, 1 oxygen. So this will be twice in terms of the value. So you times it by 2. It's giving those values here. The value of potassium ionization is that one, because there's 2 of them, so you multiply by 2. So now you got potassium ion plus oxygen gas, and you got 2 electrons, because 1 for each potassium. That's 2 electrons. So now what you want to do is get that electron and give it to oxygen. So because you're giving the electron to oxygen, we call that enthalpy of electron affinity. So that makes you making the oxygen atom gas become oxygen ion gas. So that's the first one. You give it the first electron. To give it the second electron, the energy goes up rather than going down, because when you're giving an electron, it's exothermic, and that's why it goes down. But now to put another electron there, that electron will repel that electron, which means that you have to do work to put the electron in there. You have to give it more energy. Because of that, that energy goes up. Because now you're not doing work to put the electron there because of repulsion. That electron will repel that electron, so you want to force it in. So that's why you get that. So now you got O with 2 electrons, negative charge in there. So that's stable state. That's octet now. This is potassium now. Plus, again, that's octet, so that's stable. So the two come together because of the two ions, electrostatic force of attraction, to now form the potassium oxide solid. So the gaseous potassium ion and the gaseous sodium ion, the cation and anion attract together, electrostatic force of attraction, and then you get the lattice entropy. That's again because it's negative, because they are making bond. So this is making bond. Just remember that this one is minus 141 because your first electron affinity, because you're adding electrons, so you're making, it's like this is making of, so when you're making something, that's negative. But the second making was more difficult because of repulsion, so that it's positive. So that's 790. Now this is what we need to find. So part 2 says calculate the lattice entropy of potassium hydroxide. Also, this is minus, because this is 0 and this is below 0. So this will be minus 363 for the entropy of formation of potassium oxide. You can see there is minus 363 because it's going down. It's below 0. So again, this is making, that's exothermic. Part 2, calculate the lattice entropy of potassium hydroxide. So basically we want to calculate the value of the lattice entropy here. So in this case we can say, okay, so for part 2 we use Hess's law. Hess's law states that we start from 0 here, and this is in the path goes from 0, we go all the way there, back up there, and then back there. So that's the first journey. Okay, that's indirect route. And the direct route is just going from there to there. So this is direct route, and that's why minus 363, because that value is minus 363. And that value is equal to, that journey is equal to that journey all the way there to there. So that's what Hess's law is saying. So with Hess's law, I start here, which is this one here, and I go all the way there. So I need to add all those together. I need to add that journey together. So that's one, this is indirect route, and that equals to the direct route. So that's what we're doing. And here is minus 363 is that one. And then we're adding this one here. And then we're adding 2 of those. There's 2 of those. And then we're adding that one here as well. And then we're adding that one. Even though it's negative, we're still adding it. So plus minus 141, which of course it will be minus here because plus minus is minus. So, and then we're adding that path as well, which is 790. So that's the path 790 we're adding. And then we're adding this one as well. So that'll be delta HLE. So all the one that goes like that, we have to add them, and that'll be equal to that one. So that's what we've done here. And then when you add all this together, you get that plus this one, and you still got minus your minus 363 on the left. So to find this one, I need to move this to the left, and therefore I get delta HLE equals minus 1914, which is now become minus, and then this is already minus. So altogether this is minus 2277 kilojoules per mole. So that's the enthalpy to make this of the 2 positive potassium coming together with the negative 2 minus to come together, the electrostatic force of attraction to make this. So that's why it's minus, because you're making it. But to break it, if you want to break the solid, that will be the same energy required, but it will be positive because breaking requires energy to be put into that structure here. So therefore, it will be positive if you want to break it, that's endothermic, but to make it, it will be exothermic, which is minus 2277. E, a similar Born-Haber cycle to to potassium hydroxide in D can be constructed for sodium oxide. The first ionization energy of sodium is more endothermic than that of potassium. Explain why. Yeah, sodium, if you look at sodium, it's in the third period and potassium is in the fourth period. So that means that sodium is closer to the nucleus. So removing the first ionization energy will be more because it's closer to the nucleus, but potassium is further away in the fourth shell. This is a third shell. This is in the fourth shell and it's far from the nucleus, so it will be less. So ionization energy decreases as you go down the group, and that's why this one will be more shielding because you got the third is shielding the fourth from the nucleus. So that's why. As you know what I mean by shell, so that'll be first shell, second shell, third shell. The potassium will be 1, 2, 3, 4. You can see in the center is the nucleus. That's the nucleus there. You can now see that the potassium is far from the nucleus and sodium is closer to the nucleus. So the ionization energy for sodium will be more than the ionization energy of potassium, the first ionization energy rather. 2, that's E part 2. The lattice enthalpy of sodium oxide is more exothermic than that of potassium oxide. Explain why. Well, sodium ion and O2 minus ions, they're stronger than the potassium ion and O2 minus ion. The sodium ion radius is smaller and closer to the oxide ion compared to the potassium. Both of them have +1, so they both have +1 charge, but sodium is smaller ionic radius, hence stronger electrostatic attraction.